And we are moving ahead to the next poster. That's curl quantization for automatic placement of knit singularities. The authors are Raoul Mitra, Matteo Couplé, Tongtong Wang, Megan Hoffman, Kui Wu, Edward Chen, and the paper will be presented by Matteo.
Thank you for the introduction. This is joint work with Boston University, Lightspeed Studios, and Northeastern University. Sadly, first author Rahul could not travel to Vancouver, so I'll be presenting in his stead. So knitting applies to the whole garment industry. So we have standard clothing like socks and t-shirts, but also more exotic garments like these stretchy seamless fabrics or even shoes. But there's also a growing demand for technical applications like these composites, which essentially is resin reinforcement with a knit preform, which allows to introduce shaping in these like high performance mechanical pieces. So if you would zoom in on one of these knit fabrics, you would see that there's a yarn interwoven in a very special way through stitches. And we introduce a bit of terminology here. The yarn has a horizontal course direction and a vertical wale direction. And we can abstract the complexity of this yarn structure away by using a knit graph. As we can see here that the yarn can have irregular stitches that will introduce curvature in the fabric. We can have short row ends, which insert an extra row in the course direction, and we can have increases and decreases that will add or remove columns in the wale direction. And so the task we're addressing here is, given a target shape, how can we place stitch irregularities to make the knit graph as uniform as possible, so meaning uniform size and 90-degree angles. So there's a rich literature on how to tackle this problem, and all have their shortcomings. AutoKnit is robust but lacks the user control that is needed in this context. KnitKit has no guarantees on manufacturing constraints. Knit templates provides a course-quite layout, but there's no stitch-level singularity placement. And our previous work, Helix-free stripes, guarantees manufacturability, but is very costly because there's a mixed integer solve involved. So the work here will fill in these gaps by providing a fast strategy that is, because it is greedy, with an automatic placement of singularities with a flexible user control of where to place or not to place singularities. So the way our method works is by computing stripe patterns. At a high level, a stripe pattern comes from vector fields that have special singularities. And these singularities correspond to the birth and death of stripes in the pattern. And the way that these stripes will come from these vector fields is very similar to the framework of stripe patterns by Nopol and colleagues, for those who are familiar with this work. So there's going to be one stripe pattern for course and one stripe pattern for wale direction that we're going to blend together later. And so the goal here is to design these vector fields to have stripe patterns that we want. The starting point for this is what we call a time function, h. It represents the order in which the fabric is knit. So we start at h equals 0 on the tail of the duck here, and we end at h equals 1 on the head. And there's it's smoothly interpolated in between. And if we take this function and we take its gradient in the top left, it gives us a guiding field for the course rows. And we normalize this gradient field to promote equal spacing of the stripes, so to promote knit graph uniformity. If we rotate this gradient, we get a guiding field for the wale directions. And so the task here is to use those as starting points for optimization and then add singularities in there so that they form the stripes we want. The way our method works is by looking at the notion of a curl of a guiding field. Intuitively, the curl will tell us how non-integrable the vector field is. So essentially, it means where the level set spacing will change the most quickly. And we can see that if we introduce singularities in the stripe patterns or in vector field, it corresponds to impulses of curl. And so by inserting singularities, we can allow for more even spacing of the stripes, which is exactly what we want for knitting. And so our idea here is to concentrate or quantize the curl to a discrete set of singularities that will eventually correspond to stitch irregularities. And from this perspective, we can see that the continuous curl of the original guiding field is a good heuristic on where to place singularities. As a side note, we're actually inserting what is called in other contexts position singularities. which introduce a new layer in a quad-dominant mesh. And so we can make a parallel here because we can see that curl leads to position singularities, just like Gaussian curvature leads to the traditional rotational singularities that we see in quad meshes. Ultimately, we formulate this as an optimization problem where we're trying to find a vector field V and singularities P1 to Pn, such that V will be as close as possible to the initial guiding field, which is this normalized time function gradient. And we want to constrain the curl to be 0 everywhere except at these singular points that will correspond to impulses of curl. Now we can use the curl as a signal of where to place singularities. And this leads to a very simple algorithm. You look at the continuous curl, you find a point with a maximum absolute curl, and you place a singularity there. And this will concentrate the continuous curl into a curl impulse at this singularity point. And if the curl is positive, so the red areas, we're going to have an increase in the well pattern. And if the curl is negative, we're going to have a decrease. And we repeat this greedy procedure until the objective, which is fidelity to the guiding field, not only in orientation, but mostly in equal spacing, until this objective stops improving. And in a course direction, we need to be a bit more careful because there are some manufacturability constraints that we didn't touch on, but that are detailed in the paper, this famous helix-free constraint. We achieved that by using the path integral constraints that we developed in last year's paper, Mitra 24. And these manufacturability constraints are the reason why we cannot use a standard quad-dominant measure for this task. So once we have these optimized stripe patterns for coarse and whale, we can intersect them into a knit graph, which is the quad-dominant mesh we're looking for. And so in here, we'll have the pink pentagons that correspond to short row ends, and the green triangles are whale increases and decreases. And by construction, this knit graph is guaranteed to be machine knittable. Here are some of our results. We consistently produce knit graphs that are uniform and as uniform as possible and machine knittable. And we also offer and route a render tool at the yarn level. And this render is smooth without any yarn relaxation thanks to a global placement of singularities, which is something that previous works like AutoKnit could not achieve. And naturally, we were able to schedule these knit graphs using AutoKnit to send them to an actual knitting machine and produce these knits that you'll be able to see at the poster session. We provide some figures about the size of the support mesh and the runtimes. And what's important to see here is that compared to previous work, Mitra 23, we are between 30 times, 100 times faster, which is great for people wanting to use our tools. Last thing I want to mention is that we can accommodate, the methodology we developed allows to accommodate specific user control through curl signal editing. The way it works is that if a user doesn't want stitch irregularities in specific regions, for example, because there should be a logo or some color work, we can simply mask the curl measure and set it to 0 in that region. And naturally, we can create seams, which are sequences of increases and decreases in the whale direction, in some specific places by just boosting the curl signal where the seam should appear. These features set our method apart from previous works, and they're important to users. So to conclude this talk, we propose a method for designing manufacturable knit graphs that is fast, fully automatic, and flexible regarding user constraints. The key insight here is that the vector field curl serves as a signal of where to place singularities, which reduces the problem to a curl quantization task that we approach using a very fast, greedy strategy. In future work, there's going to be two things we'll be tackling. The first one is to make the strategy truly global, meaning optimize all singularities simultaneously to avoid suboptimal placement choices early in the process. And the other thing is to design better guiding fields, because we can observe that the default guiding field, which is the normalized time function gradient, can be sometimes a poor guide for some models, like this fertility model on here. And so one idea is to optimize the guiding field and the knit graph in a joint fashion. And lastly, before leaving, I want to mention that Rahul, the first author on this paper, is looking for work, so definitely check out his website and reach out to connect if that is interesting. Thank you for your attention, and please come to the poster session to talk more.
Thank you. So if you have questions, please spare them for the interactive discussion. And